Responsiveness is the key attribute of networked systems in which the users are interested in getting a timely response to their queries. In this module, we shall understand what is formally the response time. We'd look at the measuring points, the locations where we are going to determine the response time, and we are going to look at an interesting mathematical representation of it. Response time per se is a relative phenomenon. Response time requirements are determined by the end user or the application using the networked components. Formally speaking, response time is the amount of time between a request sent and the response served, and all the intermediate time that elapses between the two. The measurement of response time is highly dependent upon where exactly we are looking inside the network. An interesting paper by Tim Norton titled End-to-End Response Time, Where to Measure, presents a figurative scenario in which you see that there is a client PC with client software shown as C1 and dialog boxes shown from D1 to D3. The client talks to a server. The server S1 talks in turn to other servers S2 and S3, which in turn talk to database server 1 and database server 2 respectively. Here you see there are arrows shown for the messages which are sent and the messages which come as reply, and these are labeled from A to V. It is interesting that if a client is interested in seeing the response time between A and B, he is trying to evaluate the performance of dialog box D1. Similarly, if the client is interested in interactions between client C1 and server S1, the client would look at the interaction and the response time elapsed between G and H. And as a worst case scenario, a client could be interested in sending a message from A on top left and receiving a final reply in F. This might involve all the interaction from the client to one server, S1, which in turn talks to the other servers S2, S3, and all the database servers shown here. Two interesting works, one by Reinder Brill, System Architecture and Networking, these are his lecture notes available, and Mikhail S. Jodin and Hans Hansen, Improved Response Time Analysis Calculations. In these two works, the authors have tried to identify and measure the response time quantitatively. First, let's look at the under discussion scenario. Here, various tasks as TOR1, TOR2, TOR3 are represented in alphabetical order as TOR-I, TOR-K, TOR-J, TOR-L, mu-J. Here you can see that it is a periodic system and the task in CPU1 is going to activate task in CPU2. In CPU2, there are two tasks, TOR-K and TOR-L. In order to activate one task from CPU1 to another task, CPU2, there is a message called mu-J, which is sent on a bus. There is a probability that the task which gets completed on CPU1 results into finish jitter, that results into an activation jitter, also called the activation jitter is also termed as the receive jitter, is going to activate the tasks in CPU2. So there is a kind of finishing and activation jitter, which is going to result into an overall end-to-end delay in the response time. The activation jitter, also known as the release jitter, is going to determine the overall performance of the system when the task Ti is initiated and task TL is concluded. Mathematically speaking, The response time can be measured as the worst case response or computation time, which would be dependent upon the maximum blocking time from low priority processes, the worst case computation time of the event, the set of processes with higher priority than I, the maximum jitter variation in the activation times, the period or the interval over which this response is being measured, and the worst case computation time for the other processes. Here you can see that there's a ceiling function. This ceiling function represents the maximum number of preemptions which are done by higher priority processes. So it is going to have an adverse effect on the response time for the process under consideration.